Hello all, my name is Serdar DURDAÐI. I am the Dean of School of Pharmacy at the Bahçeşehir University. I am leading the Computational Biology and Molecular Simulations Lab at the Department of Biophysics, School of Medicine, Bahçeşehir University. So if you like to have more information about my lab and our research, you may visit our webpage, durdagilab.com. And you may also send me email that I have written here, my email. So today I would like to talk about our recent work, which is new methods in silico methods to accelerate the transition from preclinical to the clinical stage. So as you all know, the development of new methods and novel ideas in silico approach to accelerate the transition from preclinical to clinical stage needs lots of effort. And in the last few years, there are lots of new approaches to improve the success rate of the drug design that is actually initiated with the in silico methods. So far, we have, for example, in the visual signaling, we have AI accelerated quantum chemistry, machine learning property prediction, and of course, there are also development from the computational part, like we are now using lots of advanced GPU and CPU technologies. But still, there are lots of space that one can increase and improve these steps. So today I would like to talk about a bit glioblastoma and what we have done regarding with this disease, which is quite serious disease. So glioblastoma is an aggressive type of cancer that begins in cells, and it is called astrocytes that support the nerve cells, and it can form in the brain or spinal cord. Glioblastoma is also known as glioblastoma multiforme, or shortly GBM. And gliomas are common primary brain tumors, which are representing almost half of the whole brain tumors with highly aggressive and invasive properties. And gliomas constitute the second most common cause of the death from intracranial diseases after the stroke, and they have very dynamic heterogeneous tumor tissues consisting of tumor cells with uncontrolled proliferation, inducing angiogenesis and escaping the host immune response. Gliomas' intratumoral heterogeneity and diversity of the tumor-associated molecular defects led to treatment resistance and tumor recurrence triggered by the cancer stem-like cells. The present therapeutic approach aims to target tumor drivers such as specific gene defects and oncogenic signaling pathways, but these approaches have very low efficiency. Around 50% of glioma patients are diagnosed with GBM. The WHO World Health Organization grade for glioma, which is the most aggressive brain tumor in adults. The difficulty in treating gliomas is primarily due to the invasion of the tumor-containing cell populations. Despite extensive treatments, including surgical resection, radiotherapy, and chemotherapy, GBMs tend to be recurrent and fatal, with a median survival of around 1 year, unfortunately. Studies show that GBMs display the worst prognosis, with only 10% of the diagnosed patients surviving for 5 years. So in this disease, one of the enzymes, which is called IDH1, isocitrate dehydrogenase 1, mutations cause an oncometabolic gain of function. Certain somatic mutations at crucial arginine residues in IDH1, which is cytoplasmic, are common early driver mutations in glioma and acute myeloid leukemia. These mutations are unusual because they cause the gain of novel enzymatic activity. Instead of isocitrate being converted to alpha-ketoglutarate with production of the reduction reduced nicotinamide adenine dinucleotide phosphate, NADPH. Alpha ketoglutarate is converted to 2-hydroxyglutarate with a consumption of NADPH. 2-HG builds up to high levels in tumor cells and tissues of affected patients and supports tumor progression by a mechanism that is yet to be determined. So in this study, we actually try to understand mechanistically with two different ways. The first way was construction of the cell line-based QSAR models, and we also constructed a target-based QSAR model, which is we used IDH1 mutant inhibitors. So here you can see our algorithm that we actually used in this study. First of all, we actually constructed the machine learning algorithms, and then we screened around 500 million small molecules using these algorithms. And we also used text mining in order to speed up the studies. We also conducted binary QSAR model studies to understand the therapeutic activity track and also to predict the physicochemical properties such as ADME properties and also toxicity profiles. Then selected compounds are docked at the IDH1 mutant binding pocket, and we again used some criteria to filter out the molecules. And for the last step, we used selected compounds in the molecular dynamic simulations to better understand their structural and dynamical profiles. Finally, we ordered a couple of molecules, not a couple of, actually, it's like we ordered more than 10 molecules for checking their biological activities using different in vitro assays. So here you can see more details, how many molecules we used. By the way, together with the machine learning based QSAR model, we also constructed classical 3D QSAR models to check the to check and compare the statistical results of the constructed models. Regarding with the text mining, we actually try to speed up the simulations and also screening steps. So for that reason, we checked truly the IDH1 mutant inhibitors, and we found that in the CAML database, when we checked the compounds, we found that there are 3 crucial pharmacophore units, such as oxazolidine, benzamide, and primidine, that these are the pharmacophore groups, or let's say the key fragments that IDH1 mutant molecules are carrying these pharmacophore units. So for that reason, initially we downloaded the small molecule database from Zinc 20, which includes about 157 million molecules, but after the ligand preparation, this number also increased more. And also we used a SPECS database that have around more than 200,000 compounds. So we checked how many compounds we have the compounds actually includes and carry these fragments. For example, among 157 million molecules, there's only 3.9 million benzamide, the compounds that includes 3.9 million with the benzamide, and we focused only these 3.9 million molecules. Or if you check the oxazolidine, we have only 543,000 compounds, so we just focused these compounds. For the specs, we directly pass to docking because we have less number of molecules, such as around 200,000 compounds. Together with these molecules, we also screened natural compounds, lichen secondary metabolite libraries, database, and FDA-approved compounds from MPC. So we also put a threshold of PIC50 because these QSAR models actually predict the compounds PIC50, the minus log IC50 values. So the value that we put is 7, which is a reasonable number that we can actually filter the compounds that have the less than 7 PIC50. Then we use these compounds in the docking at the IDH1 mutant enzyme, and the compounds that have the better docking score than -7 kilocalories per mole is used in the MD simulations. In order to decide which compounds we will use in the MD simulations, we actually performed normal distribution analysis using the docking scores and PIC50 values and phase fitness scores. And based on this Z-score analysis and MDA analysis, we decided how many compounds we can actually put in the MD simulations. So first model that I would like to mention is the cell line-based model, which is we used U87 and U251 glial cell lines. The data we actually received from the Campbell database, IC50 values and their corresponding structures. First of all, we prepared the structures, and then we tried to construct the models. So the first model actually includes 172 molecules, and we divided the molecules to two groups. 67% is the to construct the model, and 33% is for the testing the molecules. For model generation, these 116 compounds were divided to 70% to 30% training and test sets. And to validate the model, we also used external test sets. And for this, we collected 160 molecules that we know their IC50 values from Campbell database against they used this U87 cell line. So these 169 molecules are not used in any point in the construction of the model, so they are truly unknown molecules. So we are just trying to see how the predictive power of the our model is strong. So here you can see the statistical results. So we have the R score is 0.72. The top model that we received was KPLS radial 15. And our standard deviation is around 0.4, R square is 0.89, and Q square value is 0.80. So here you can see the training set and test set. The x-axis shows the observed PIC50 values. It is the experimental results, and y-axis shows the predicted PIC50 values by the model. And our R square value, as you can see, it is 0.89. But we want to see if this model how this model actually predict well with the external tested molecules. And as I said, we used 169 molecules, and the R square value was 0.53, as you can see. For the first model, for the second model, we used U251 cell lines. So this is the model set 2. And 144 inhibitors were used for the model building and validation. And of these 144 molecules, 88 were selected for the model building, and 56 molecules were used as an external test set molecules. And here you can see the statistical results. Now our R square value is quite large, quite good, 0.90, and Q square value is 0.89. Actually, similar with the previous one, as you can see here, but the Q square value is better than the previous one. So it looks like using the U251 cell lines gives a better result. And here you can see the external test sets. The R-square value is 0.79, which is very good. So it looks like this model that we constructed actually gives us very good prediction. Here again, for the model construction, we used KPLS, and for the fingerprint type, we use Molprint 2D. So here you can also see how we can use this constructed model to design new molecules. We can actually label and color each atom with positive contribution and negative contribution. So here I colored positive contribution to the activity as green and negative contribution to the red. So this means that if you remove this part with other fragments, or if you remove at all, you may increase the activity. And here, for example, if I remove this part from the ring, the activity is increased from 7.7 to 7.11. We also used classical QSAR, and for this we used phased program, and we constructed 5-sided and 6-sided models. Here you can see the R-square and Q-square values, which is more than 0.7. And we also try to see how these constructed QSAR models actually perform with the external validation, external test set validation. Unfortunately, as you can see, the model, although they are reasonably good, they couldn't predict the external test set molecules very well. So the one that we received from the 4-site match with the ADHRRR, the 6-sided model was around 0.4. Here you can see the example of the docking and PIC50. So we used normal distribution curve, and we try to get the high docking score and very good PIC50 value. So for the PIC50, we used the Z-score threshold of +2, and for the docking, we used -2. So then we try to see what are the common compounds with among these two groups, and we use only these compounds in the further analysis. So here you can see the positive control compound, which amino acids actually the molecules and amino acids making the nonpolar interactions and polar interactions, non-covalent interactions. And here we can see one of our identified compounds at the binding pocket, and we try to see if we have common amino acids. So this is the reference molecule from the PDB structure that we use, and this one is the molecule that we identified. After the MD simulations, we run MMG-BSA calculations, and we calculate the average MMG-BSA. So we run for each compound 500 nanosecond MD simulations, and we collected 500 frames, and then we calculated the MMG-BSA during the 500 nanosecond MD simulations. And here you can see again 2D ligand interaction diagram, which amino acids actually stays contact with the binding pocket amino acids during the MD simulations. By the way, here you can also see that all of our compounds, almost all of our compounds, show a better average binding energies compared to known compounds, such as IDH 305. So this IDH 305, one of them is in the chain A, and the other one is the chain B. But most of our compounds shows a better performance than these two, this compound. We also run per-residue interaction analysis to see which amino acids contribute more to the binding affinity. So you can see that tryptophans are very important, such as tryptophan 124, tryptophan 267, tryptophan 285 is very important. So they have very good contribution to the binding affinity. We also try to see which fragments from the selected heat molecules have smaller or larger contribution to the total binding affinity. So from this, you can see that, so each color shows each fragment here. For example, here, you can see that this orange colored fragment, F2, has the smaller contribution to total binding energy. So this means that you may want to adjust, or let's say design new molecules from F2. So then we ordered more than 10 molecules, and different in vitro assays are conducted. For example, here we can see that you can see the inhibition of the spheroid formation of the U87 cells. So as shown here, so the y-axis shows the relative colony area, and here we can see the heat compounds that we tested, especially heat compounds 1, 4, 5, 6, and 7, and 16 at the dose-dependent manner actually works very well, and 90% less spheres were formed in the U87 cultures treated with these heat compounds. And here the pale blue shows, the cyan color shows the 5 macromolar of these heat molecules, and blue color shows 10 macromolar of these compounds. Likely heat compounds 4, 5, 6 also showed complete suppression in the U251 cells. However, in contrast to those in U87, heat compounds 1 and 16 partially inhibited spheroid formation of U251 cells by 60–70%. Heat compounds 7 and 9 only partially suppressed spheroid formation in both U87 and U251 cells. We also checked the suppression of aerobic glycolysis in U251 and U81 cells. So here, actually, the effect of the compounds on metabolic energy production studies were examined using the extracellular flux analyzer by measuring 2 major cellular energy producing pathways, glycolysis and mitochondrial respiration. And we assessed glycolytic proton efflux rate in GBM cells based on extracellular acidification rate. And shown in the figure, glycolysis parameters including basal and compensatory glycolysis were decreased by treatment with heat compounds 1, 4, 5, 6, and 7 in U87 cells. And again, if we check this similar and same analysis with the U251 cells, especially heat compound 4 and 5, shows very promising results. We also checked the proliferation toxicity assays, and here you can see the result. So 11 heat molecules were tested for proliferation assays, and it was observed that 10 molecules other than heat 11 were effective at 100 macromolar concentration, and especially heat 1 and heat 14 were also found to be effective at 1 macromolar concentration. According to these results, it's estimated that effective values of heat 1 and heat 14 may decrease to nanomolar levels. For these molecules that are very effective, we actually try to understand their effect with stirred MD simulations and umbrella sampling method. So in this method, actually, it can be considered that what is the force which is needed to break the bonds from the binding pocket of the ligand from the active site. So here you can see that if you compare the heat 1, heat 4, heat 5, heat 6, heat 7, and with the IDH 305 reference molecule, which is shown with the pink color here, all of the compounds is needed larger work compared to reference molecule. That shows that so in order to remove these small molecules from the binding pocket, you need to conduct larger and larger forces compared to reference molecule. So we also perform visual drug repurposing study, and for that we conducted we used FDA approved molecules, and we conduct our simulation with using the ligand-based method, structure-based method, and for the selected molecules we run MD simulations. And finally we found that these 4 molecules, dequalinium, conivaptan, tazamostat, and terostrat ethyl, shows very promising results compared to reference molecule. So here you can see 3D and 2D ligand interaction diagrams, and which amino acids actually contributes to the binding. So here actually what we did, initially 197 IDH1 mutant inhibitors were downloaded from Camel and were used for the model construction. So as I said in the beginning, together with the cell line based QSR models, we try to also construct the QSR models using the target based target spell. So for that reason, we used IDH1 mutant inhibitors. So 197 IDH1 mutant inhibitors were downloaded from the Campbell, and another 85 compounds were used as an external test set to validate the model's predictability. And in this approach, PI50 values was used as a Y variable to make predictions, and physicochemical properties were used as X variables to train the neural networks for predictions. 77% of learning set was divided into training set, and 23% was used as internal test set. And here you can see the predicted PI50 value and experimental PI50 value. The R square is 0.73 and Q square is 0.63. For the external test set, the R square value was found as 0.56. So results from visual drug repurposing studies show that these compounds, especially using the neural network, dequalinium, conivaptan, tazomostat, and pentagastrin, can be a good candidates against brain tumors. So these molecules actually are using for the different aims, but our in silico results shows that they can be considered to test them in vitro against the GBM. Okay. I think I can stop here. I'd like to thank all of my colleagues to run this experiment and simulations, and thank you for your listening.